Hello, I would like to welcome you. In today's class, we will discuss insertion sort, which is basically sorting using a sorted list as an abstract data type or a sorted list implementation of the priority queue. So the idea here is given an input sequence S, let us say 4, 5, 1, 6, 2. You create an auxiliary data structure, a priority queue P, which is initially empty, and the idea is to scan the list S and insert elements in the order in which you scan into P. So this makes P 4. When you add the next element 5, you ensure that P has an increasing order of elements. So which means you are going to append 5 to the list, you will get P equals 4 and then 5, and then for the next element obviously you will need to prepend P with 1, that is 1, 4, 5 and so on. So as you can see, the scanning of the list will be order n, but the insertion into P can in the worst case take n squared time summed up across all the insertions. So for the first insertion you will have incur a complexity of 1, for the second one which is 5 you need to scan 2. In fact you will have to incur 1, 2, 3 up to n irrespective of how well arranged the elements in S are. So this is the order n square insertion time. As far as deletion is concerned, all you need to do is pick elements from P starting with the first element and pick the minimum element and insert them into S. Now what will this mean? Well, this will mean just a linear scan because P is already sorted. So you have 1, 2, 4, 5, 6, and all you need to do is push them in the same order into S. So this is order n, whereas insertion was order n square. Overall the complexity is order n square because it is dictated by the more expensive insert. Now this naive implementation of insertion sort should ring some bells. You should probably consider getting the sorted content of P straight away into S without having to populate a separate P. Why? Because you notice that in the process of obtaining a sorted S you have actually first created a sorted P. So that gets us to the in place version of insertion sort, and let us understand how this functions. So as explained earlier, you will still have S which is 4, 5, 1, 2, 3. The output is to get the same elements in S but sorted in increasing order. So what you do is as follows: you maintain the key that need to be inserted, and of course you get these keys in increasing order of the indices. So you start with key equals 4, I is 1. The goal is to insert 4 into a P. Now what is this P? For us the P will correspond to a prefix of S. So this prefix will basically be S elements from S ranging from indices 1 to I minus 1. So your initial index was I was initially here at 4, I equals 1. So initially the prefix P, which corresponds to S1 to I minus 1, will be empty. But going forward, for I equals 2, this will be just 4. So for the time being, we focus on the key at 4, at 5. So P equals 4 and K equals 5. This is again when I equals 2. So what you do is set the index j equals I minus 1. The idea is to scan P starting from the rightmost element. So as long as you have not hit the leftmost index of S or P basically, so while j greater than 0, and till a point where you find that the jth element of S turns out to be greater than the key, you basically keep shifting the elements of S of B. Why are we doing this? So let us understand with respect to the example. This is saying shift the elements of P to the right to make space for K until, so you do this until you find that Sj is already less than equal to K. So what happens in this case? Again let us see. So for j equals 1, I equals 2, you are only interested in the prefix ending at 4, and you find that 5 is already greater than 4, greater than equal to 4. So in this case what happens is as follows: you will need no shift. So the array S after this iteration will remain 4, 5, 1, 2, 3. But for the next iteration you will shift your focus, the I to be 1. Now when you again try and insert I into the prefix P preceding I, you find that I is less than 5, I is less than 4. So what you will have to do is accommodate this I by right shifting the prefix members of S. So this will need a following transformation. So this will mean S will need to make space for 1, 4 and 5 shifted, and then place 1 will be occupied by S, and that is exactly what happens when you set Sj plus 1 equals K. 2 and 3 are unaffected. So this specific insertion is happening here, Sj plus 1 equal to K. You stop when you have no element to the left that is greater than the element K that is being inserted, and in this case there is no such element at all, so that the only place you can insert 1 is here. So I hope you understand the working functioning of this specific algorithm. Is this correct? What is its complexity? Let us discuss that next. So correctness first, and here is a claim for correctness. We discussed in terms of a loop invariant. At start of each iteration of the ith repeat loop, the subarray S ranging from I equals 1 to I minus 1 consists of elements of the old S1 to I minus 1 but sorted in ascending order, right. This is what mimics the priority queue. So what are we doing here? So let us understand quickly what the correctness of this invariant at initialization. So initialization, yes, indeed this holds, because you initialize with I equals 1, which means there is an empty list prefixing up to I minus 1. So initialization holds. Maintenance, so if this invariant holds before the ith iteration, or rather the I plus 1th iteration, will it hold at the I plus 1th iteration? The answer is yes. Please note that the I plus 1 iteration is only going to compare the key at the I plus 1th position with all elements preceding it, and we are already assuming that the preceding elements are sorted. So you scan from the right to the left until you find an element in S1 to I minus 1 that is actually less than the element, less than equal to the element or the key that is being inserted, right. And because you stop at that position, and because you know from the previous iteration that elements preceding the element that was found to be less than equal to the key are already sorted, you can stop, and in fact this also ensures that the loop invariant is maintained. So the maintenance holds since S from 1 to j is sorted. This is referring to the algorithm shown in the previous slide, and we already found that Sj was actually less than or equal to k, and since Sj plus 1 is going to be containing the key k, and the elements after Sj plus 1, that is Sj plus 2 to I, are already sorted and shifted. And they were all found to be greater than k. So this ensures that maintenance holds. The third property is termination. Again, this is very easy to verify. Typically is a maintenance property that requires some work. Analysis, we are going to look at the number of times each step of this algorithm is going to be invoked. So we have an initialization, order 1 complexity. You are going to iterate over all keys k except the last one actually. I mean so the complexity can be treated as n minus 1, the iterations require n minus 1 computations of k equals Si. Thereafter for each I you might have a variable number of shifts. So what you see here is a variable number of shifts, by, and specifically by shifts you mean right shifts, until I repeat until you find an Sj which was less than equal to k. So this variable number of write shifts we refer to by Wi. Of course there is one more additional step which is inserting k into Sj plus 1. So this gives us Wi minus 1 repeated n times, and finally once you have actually substituted Sj plus 1 equals k, doing this n minus 1 times, we can go ahead and sum up all these individual counts. So complexity given by this expression involving various constants. The only thing that needs to be elaborated a bit upon is what happens to these summations in the worst case, what happens to these summations in the best case. Everything else seems to be order n. So best case running time, what will be the best possible scenario for Wi's, which is there a way that you can avoid shifting altogether? Can the Wi's be basically 1? And it turns out that if your S was already sorted, so let us consider S equals 1, 2, 3, 4. So it turns out that when you try to insert 2 or 3 or 4, you end with just one comparison. So as a result, the best case running time is when the Wi's are 1 for all values of I. As a result, these terms do not contribute anything at all. There is contribution from this term, but it is again Wi, so just n times C6. So you will have n times C6, the rest is as was discussed earlier, and this all turns out to be just order n. How about worst case running time? So consider a list sorted in descending values, so 5, 4, 2, 3, 1. When you are inserting a 4, you will need to go all the way to the left, in fact hit the leftmost wall and put a 4 there. So for any of the elements, whether it is 4 or whether it is 2, you need to go all the way to the left because you know you are dealing with this new smallest element. So in all these cases, for the Wi for I equals 2 will be 2, then Wi for I equals 3 will be 3, and so on. So Wi will basically be I. So making the required substitution, you find that you will have a n into n minus 1 by 2 because you are dealing with summation I minus 1 I equals 2 to n. Likewise for the factor involving C5 and so on. So overall this is order n square. A question is there something in between? What about the average case? To discuss the average case, we will need to understand when exactly does insertion sort do a swap. So the most critical component of the insertion sort algorithm is a swap. And what is a swap? It is basically saying Sj plus 1 is Sj followed by Sj plus 1 equals k. So what are we doing? We are saying that 4, 3, 2. So if I had to insert 3, let us say the list was 1, 2, 3, and I was trying to insert a 3 here. How far will I need to go? So for every distance, every element I cross, for example I cross 4, I am basically shifting 4 to the right. So I need to shift, or rather do a swap corresponding to every inversion. And what inversion is basically an I index less than j such that Si is greater than j. So 4 happened to be greater than 3. This inversion led to a swap, but the swap is very indirect. You attain the swap by shifting and then substituting, a series of shifts and a substitution. Okay. So it is important to note that swap is realized through a series of shifts and a substitution, and this occurs for every inversion, for every pair of indices ij, I less than j, such that Si is greater than Sj. We will see that there are other algorithms which are based on comparison which do not have to do a swap for every inversion, but unfortunately that is the case for insertion sort. So the number of operations is therefore the time required to scan each element plus the number of inversions. What is the average number of inversions? So let us say I is the number of inversions, then the time complexity is order n plus I. We will try and come up with an expression for I in the average case. We already know that for worst case the number of inversions I is order n square, for best case number of inversions is 0. The claim is that average number of inversions in a list of n distinct elements is n into n minus 1 divided by 4. How did we come up with this number? So here is some analysis. So we will try and factor out redundancies in counting by clubbing together an array and its reverse. So factoring out redundancies in counting by clubbing together S and its reverse. Okay, let us see how that helps us. So pair of elements E1 and E2 will be inverted in exactly one of S and SR. This is obvious. So if E1 followed by E2 is the correct order, desired order, it will reflect in S and the reverse will reflect in SR or vice versa. So the total number of such pairs inverted in either one of S or SR, and that is the advantage of clubbing we already see, is n into n minus 1 by 2. Basically this is n choose 2 because there are n choose 2 such pairs. So they have to be inverted in one of them. Right. So what we do is we will consider the total number of such pairs inverted in one of them, and therefore the total number of inversions across all permutations is this n choose 2 factor multiplied by the number of such sets of sequences. So this is number of permutations, but factoring out the reverse of each permutation. So we do not want to count the permutation and its reverse separately, that is why n factorial by 2. So what will be the average case? Well, the average will just be the ratio. So take the total number, this is the total number of inversions, and consider the total number of permutations. So this ratio turns out to be n into n minus 1 by 4. So effectively all we are saying is the number of pairs inverted in one of S or SR is n into n minus 1 by 2, and we know that this contributes to half to SR and half to S. So therefore half of this should actually be the average number of inversions. That is an easier way of rationalizing. So the average time therefore the average number of swaps therefore is exactly the average number of inversions, and this happens to be order n square, and this is true about any swap based algorithm that basically removes one inversion in a single step. So here is a summary. The best case running time insertion sort is order n, worst case is order n square. Average again turns out to be order n square, and we are not too happy about this. Can we develop an alternative that gives better average and worst case running times? In other words, can we avoid so many swaps, or rather a swap corresponding to every inversion? So note that we used very naive property here, that we wanted the prefix to be always sorted. Can we relax that condition and avoid swaps corresponding to every inversion, and in fact implicitly attain restructuring of the array through something like a min element preceding all the other elements, because that is what we really want. We want that a min or a max element precedes other elements, and the ability to deal with all these min or max elements at a later stage. So that is exactly what we will discuss next. It is the heap sort algorithm, and that is based on the heap data structure. Thank you very much.